Okay, so this is the final section of chapter 12 that we will be looking at. And we will be looking at gas mixtures and the law of partial pressures. What's a partial pressure? Well, it's the pressure that a gas in a mixture would exert if it were the only gas present in the same volume and at the same temperature. So Dalton's law of partial pressure says that the total pressure of a mixture of non-reacting gases is equal to the sum of the partial pressure of the individual gases. So we can generalize that law to P total equals P1 plus P2 plus ... for however many gases there are in the mixture. And it can be applied to any mixture of gases. So essentially it just says that all the pressures of each individual gas make the total pressure of the gas. So let's look at an example of how we would use this law. A mixture of gases is composed of nitrogen with a partial pressure of 300 kPa, oxygen with a partial pressure of 200 kPa, and carbon dioxide with a partial pressure of 400 kPa. What is the total pressure of this mixture? One final point, yes, of course, the pressures must all be in the same unit, which in this case they are. So our pressure of nitrogen is 300. Pressure of oxygen is equal to 200. And the pressure of carbon dioxide is 400. So what is the total pressure? So PT is equal to P1 plus P2 plus P3, which is 300 kPa, 200 plus 400, all with the unit of kPa. Add those all together and we get 900 kPa. Okay, so that's it. That is how it works. The total pressure of the mixture is 900 kPa. Okay, so that's partial pressure. But we can also use this law and percentages of gases in a mixture to determine the pressure exerted by a single gas. So it's just a variation of the above question. So in example 2, we say we have a gas mixture that contains 12% neon, 23% helium, and 65% radon. If the total pressure is 116 kPa, what is the partial pressure of each gas? So this is our total pressure. So to find the pressure of each one, we simply need to find the 12%, for example, of 116 to find out how much neon is in it, 23% of 116 to find out how much helium, and 65% to find out the amount of radon present. So we write down our givens, proper form, 12% of total pressure. Helium is equal to 23% of the total pressure. I'm just gonna fix my little helium here. And the pressure of radon is 65% of the total pressure. Okay, so what is the total? And the total pressure is 116 kPa. Okay, so pressure of neon is equal to 12 out of 100 times 116. And so that's equal to, you can do your own way of finding out percents if you like. That's what a percent is, 12 divided by 100 times 116. So 13.9 kPa. The pressure of helium is equal to 23 out of 100 times 116. So 26.7 kPa. So So of course we could add those two and subtract from 100 to then find our answer as well. It's another valid way to do this. But I'm just going to continue with the numbers given. $75.4. If you're wondering if you hear some banging in the background, that's some work being done in my basement. Okay, so therefore the partial pressures of the gas mixture are 13.9 kPa neon, 26.7 kPa helium, and 75.4 kPa radon. Okay? The very last bit we will look at is gas collection. So when we collect a gas in an experiment, we use a process called collecting gas over water. So essentially that involves displacement of water from a vessel. So you can see in this diagram, we have a gas collection bottle completely full of water. That would be this one right here. So, and we use a water trough or some type of container to put it in. So you fill it with water and then you invert it. And then this is a gas that's being collected from a reaction that's going on. And the gas is bubbling into the gas collection and displacing the water. Okay, so from the gas, this has little gradients on it, so markings that you could read the level of gas that's inside the container. Once the level of the gas is equal to the level of the water, that is where how much gas would be, that's how you read the gas level. Okay, so when we're doing this, we need to also take into account that there's water vapor, right? Because that would be part of the mixture. So we call this the vapor pressure of water. And this, of course, depends on temperature. Okay, this depends on temperature. So the warmer the temperature, the more the water vapor the mixture will contain. So there's a chart in your book on page 596 where we can see the various vapor pressures of water at various temperatures. So I'm just going to show that to you. I have it handy here. Okay, so here we go. Pushing over. So you see how as the temperature increases, the vapor pressure of water increases. Okay, so we have to take that into account, and this is showing exactly what we're about to do. We take the total pressure is equal to the atmospheric pressure equal to the gas collected plus water vapor. Okay, so we need to, that's what we're going to look at right now. So whenever you collect gases over water, you must consider the partial pressure of water vapor, and you have to know the temperature. So we're going to see in this next question a situation like that. So if 60 liters of nitrogen is collected over water at SATP, 25 degrees Celsius and 100 kPa, what is the partial pressure of nitrogen? So we got to write down our givens. So our volume is equal to 60 liters. Our temperature is 25 degrees. And our pressure is, our total pressure is 100 kPa. So we want to find the partial pressure of nitrogen. So since our temperature is 25, oh, you see my lovely nail, look at that, it just broke. Oh dear. So let's take a look at the chart again on page 596 at 25 degrees. Okay, what is the partial pressure of water? 3.17. So this is what we need to use as the partial pressure of water in this equation. So we'll write that down too. So the pressure of H2O at 25 degrees Celsius is equal to 3.17 kPa. Running out of room back here. I'm going to move that up so you can see it better. So our total pressure is equal to the pressure of nitrogen plus the pressure of water. So what is the pressure of nitrogen? I'm just going to rearrange this. It's going to be, move this over, so I got to subtract the water vapor from the total pressure minus the water vapor. So PN2 is equal to 100 kPa minus 3.17. I can just put a little bracket on that so I don't have to write kPa twice. So we put that in our calculator and we get 100 minus 3.17, 96.83. Okay, so therefore the partial pressure of nitrogen is 96.83 kPa. All right, so that's the style of questions you'll see. There's some questions for you to do on page 594, 596, and 597, so do as many as you need. The answers are there for you, and reach out if you have any questions. This is your final lesson of chemistry.